So let's wait 1 minute.
Okay, now I think I can do it.
Okay, great. So
Okay.
please, Carlo.
Can you see the presentation?
Yeah, we see. Thank you.
Okay. Thank you for the inconvenience. For some reason, it was not really working. Okay, thank you so much for the invitation and for organizing this beautiful series of seminars. Today, what I want to talk to you about is a very recent work that I did with some folks here at Princeton, actually my advisors and some other people from Penn State. I will show my collaborators at the end. So the outline of the talk is really already in the title. So I will start introducing from the bottom what Hyperuniform disorder is. That may be something that is not very familiar to most of you. Then I will quickly introduce the Anderson model, which maybe is a bit more familiar, but still I think it's good to make a refresh. And then I will show you the results when we combine Hyperuniform disorder and Anderson localization and see what happens. So what is hyperuniformity? Hyperuniformity is basically a way of classifying how ordered is your office. So if you have an office like the one on the left, very clean, no sheets of paper around, then the, let's say, point pattern configurations that would represent this office is like a crystal, like the one that you see below. If instead you go to the far right and you have papers everywhere, the point configurations that would correspond to this order, or better, disorder, is like would be, for example, a Poisson point process. So no correlation between the points. If instead you're in between, that probably is the case for most of us, then so the office looks ordered if you enter from the door, but if you go at a very small scale and you look at the papers in the shelves, you would see that they're not perfectly aligned and perfectly ordered. So you have a, let's say, short range disorder, but long range order if you look from afar. And this is actually the essence of what hyperuniformity is. So in a bit more precise way, how can you quantify how disordered is the system? Well, you take your point configuration in case you're dealing with something like that. You place a window of radius r, and you count how many points you have in that window. And so you keep track of n of r and n squared of r. And then you move the window around and you keep counting so that you can compute the average over different positions of the window. And then you play the same game with a bigger window so that you can scale with the distance, with the size of the window. And when you collect all your data, you construct the number variance, which is simply the variance of the number of points that you've counted in the windows, averaged over different positions of the window, and also different realizations of the point pattern that you have. So you can get different results. If you have a typical disordered system, for example, a Poisson point process, let's say, the number variance grows like the volume of the window. If instead you're dealing with a lattice, the number variance grows only like the surface. And this is quite easy to understand because if you move the window around, what happens at most is that you have an effect on the edge of the window of points entering or exiting, but the bulk stays basically the same. So it's a surface effect. But then you can have also something in between. So a scaling of this number variance, which is in between the volume and the surface. And this is what we call hyperuniform. So in a bit more precise way, the definition of hyperuniformity is that the limit for large R of the number variance divided by the volume goes to 0 in the limit of infinite R. And you can classify different types of hyperuniformity. We have class 1, in which you have a disordered configuration scaling like the surface. Then you can have a log correction, and that is what we call class 2. And then you can have something which is generally in between, and this is what we call class 3. It's actually useful to go to Fourier space. In Fourier space, what happens is that if you take the Fourier transform of the two-point function, you can basically construct the structure factor, and the statement that the number variance goes to divided by the volume goes to 0 in the large R limit corresponds to the structure factor going to 0 for k going to 0. And so what you can get if you look at the structure factor of different configurations is that if you have a usual disordered system, S of k might look something like here at the top. So if you have a Poisson point process, S of k is equal to 1 everywhere. If you have, for example, a packing problem, but that is not hyperuniform, you can have a small suppression of S of k towards k equal to 0, but still the value is not 0. If instead you're dealing with a crystal, of course, crystals are hyperuniform because you just have Bragg peaks in the positions of given by the symmetry of the lattice. So they are hyperuniform according to our definition. But then you can have disordered hyperuniform in which S of k is going to 0, in this case linearly, but you can have different behaviors. And actually, the type of hyperuniformity that I will be dealing with today is a bit special because not only S of k vanishes at k equal to 0, but it's exactly 0 in a range of wave numbers near the origin. And this is what we call stealthy hyperuniform. And why stealthy? Because if you do a scattering experiment on a material that has this type of arrangement of the atoms, what you see is that you have a region without any scattering event at the center. And this is what it's typical of crystals, because you have a region with no scattering events, and then you have the peaks given by the crystalline structure. But stealthy hyperuniform disorder have the same, let's say, exclusion region for the scattering events, but out of that is diffusive. And this is very weird, and it was not known since quite recent. So I will not go into the details of the physical properties that these materials have. They are quite surprising, and you can look at this review if you are interested. So this is basically all you need to do for today about hyperuniformity. So let me move to Anderson localization. Anderson localization was introduced, of course, by Phil Anderson many years ago. And the idea of Anderson was to find a toy model for describing how electrons move inside a material in presence of impurities. And so the model is very simple. You can describe it by an Hamiltonian like this one, and let me break it down for you a bit better. So you have two terms. You have H0, which is simply the term that allows the electron to move on the lattice. So the model is defined on the lattice, not on the continuum. And so what this H0 gives is simply a particle that can move back and forth. And then you put on top a potential, which is a disordered potential. So basically these operators, C dagger and C, are creating and destroying a particle at a given position. So if your particle is sitting at side J, the first terms moves the particle to side J plus 1. And then if you put the potential, that is simply giving an on-site value for the energy for that particle. And so the particle is moving in a disordered landscape. What is the essence of Anderson localization is that if you have a disorder which is strong enough, and by disorder I mean the variance of these Wj's numbers that appear in the Hamiltonian, if this variance is big enough, what happens is the following. Now I will show you a small cartoon of a wave function evolving starting from a position. The blue curve is in absence of disorder, so what you would get in a clean lattice. And the black curve is in presence of disorder. So you can see that the blue curve is spreading out, and so the particle is diffusing and going around. But the black one, which is in presence of disorder, stays localized in the same position, is not moving. And that's exactly what localization means. In a classical setting, this wouldn't happen. If you study the diffusive motion of a particle of a classical particle in a random potential, you will always get diffusion. The diffusion constant would depend on the value of W, but it would be non-zero. What Anderson found is that this diffusion constant can go to 0 at a certain critical value of W. In one dimension, which is actually the case that we will be dealing with, the particle is always localized, no matter how small is W, except for W equal to 0. As long as you turn on a little bit of W, the particle will remain localized. And the localization length, which is the typical size of the spreading of the wave function during the evolution, scales like 1 over W squared. This scaling is important for what I will tell you in the future. You can play the same game also in 2D. So now I'm putting two different plots for that. And you can see that W equal to 0 again spreads, as you would expect for a clean system, and W equal to 5 instead stays localized in the same area of the lattice. So this is what localization means. You can study this problem numerically, analytically. Analytically is quite complicated because of the randomness that you have in the Hamiltonian. So there's been many studies of this problem in many kind of geometries. But the essence is that, as I was saying, there is a critical value of WC for which you have localization if the variance of the random potential is bigger than this number here. And this number depends on the geometry. So in 1D, this WC is actually 0. In 2D is also 0, but 2D is the lower critical dimension. So as soon as you go in a dimension which is a bit more than 2, you would have a finite value for WC. And this can be studied both in terms of transport, as I was showing you in the animations, but also from the spectrum. So you can take the Hamiltonian, diagonalize, and see at the statistics of the wave functions, statistics of the eigenvalues, look at the repulsion between energy levels, and all these kind of things. Many of you, I'm sure, are familiar with these techniques. So now I'll try to combine the two things together and see what happens if we take the Anderson localization problem in presence of this stealthy disorder. So let's take our Hamiltonian, and for convenience we go in Fourier space, because as you remember, it's convenient to define hyperuniformity in Fourier space. So in Fourier space, the free Hamiltonian, H0, which is simply the one that tells you how the electron can move in a clean lattice, is diagonal, and so you can find which is the band in terms of the momentum. So the energy is simply -2 cosine of k. But then you trade the diagonal in the free part for an off diagonal in the let's say potential part. So what happens is that now you have your potential, which is defined in Fourier space, and now this operator here is simply killing a particle with momentum k and creating a particle with momentum k minus q. Okay, it's not assigned to the position, but to the momentum. This is typical of quantum mechanics when you go from momentum to position representation. And now we define the disorder that we would like to be dealing with, so the hyperuniform disorder. We choose it to be Gaussian, let's say, quote unquote, in the sense that these WKs, which are the Fourier transform of the real space potential, have 0 mean, which is something that is usually done. But the 2-point correlation, they're delta-like correlated in momentum, but they're somehow modulated by a function, S of q, that depends on the momentum. And we choose this function to be a step-like function. So it's 0 in a range of wave vectors around the origin, as the stealthiness prescribes. And then at some point, at some value k0 that we can tune, S of k is simply equal to 1. It's convenient for us because of connections with material science applications to denote the size of this region in which S of q is equal to 0, parameterize it in terms of chi. And this chi value goes between 0, when S of q is always 1. So that would be the typical case, the one for which I showed you the animations before, and chi equal 1/2, in which basically the system is not disordered anymore. This parameter allows you to tune between completely uncorrelated disorder and a completely ordered potential. So if you plot in real space what this potential looks like, you can go between chi equal to 0, here on the far left, in which you have a completely uncorrelated potential. And then as you increase chi, you can look at the plots and see that something is kind of happening. So you're getting, it seems like you're getting a modulation overall, and then inside that modulation, the potential is going up and down. But the thing is that this modulation is still a random number. It is still a random function, which is given by the part in which S of q is non-zero. And eventually, when you arrive at chi equal 1/2, the potential is clean, is simply plus and minus 1. And in this case, the problem is trivial in the sense that it's solved by the block wave functions. Okay, but let's see what happens in intermediate regimes. For example, chi equal 0.4, which is a quite big value. From naked eye, you wouldn't see much of correlations in the real space representation, but as you will see, it will have major effects on the properties of the system. So now our goal is to compute the localization length, which is the quantity that tells you how localized is the wave function and whether you're able to see a delocalized wave function in the system. So this part will be a little bit technical, but I'll try to be quick and go very quickly to the results. So to do that, you have to take the propagator, and we do a small W expansion. This capital W is basically the variance of the disorder. And the advantage of taking small w is that you can do a perturbation theory, which is well under control. And so the propagator that you would like to compute is this quantity here. For small v, you can do the usual Dyson expansion. I mean, for people that are familiar with quantum many-body system, this is really the basic of it. And so you can expand this propagator in powers of v, and you do it by inserting v between the bare propagators, where the bare propagator G0 is the one of the clean system, basically with v equal to 0, which is already solved because you know which is the dispersion relation epsilon k. So you can represent your expansion in terms of these diagrams here, in which G0 is a simple line, let's say a field line, and the dashed line is the potential. But since it's a disordered system, eventually you will have to take the average. And so when you make the average, what you get is that given by, since these quantities have 0 mean, all the diagrams in which you have an odd number of potential insertions will be 0. And the others will be paired because of the delta functions that you have here. And eventually, you can represent this expansion after the average in terms of a simple propagator, that we know already, plus something which is a bit complicated because it includes all these diagrams here. And this is it's known to be the self-energy. And actually, what we really want to compute is the self-energy. Why? Because in 1D is quite simple. That's why we're studying it. But in 1D, what happens is that the localization length is proportional to the mean free path, which is basically in a sense, is the mean distance between two consecutive scattering events. And this quantity is proportional to the mean survival time, which is the time between two consecutive scatterings. So there is a velocity term in between, but they're simply related. And from the general theory of many-body system, the inverse of the mean survival time is proportional up to a factor of 2 to the imaginary part of the self-energy. So that diagram in the blob that I was showing you before, if you take the imaginary part, that will give you the inverse of the mean survival time, which is eventually proportional to the localization length, which is the thing we want to compute. And let me notice that the imaginary part is non-trivial because the self-energy will include propagators, and the propagator can be split into real and imaginary part in this way. So now we look at it. We look at different orders in the perturbation theory. The first order is quite simple. You just have one diagram that you want to compute. So the dashed line is given by the disorder. It's where the potential is sitting. And the continuous line is the bare propagator. You can see that they have two different momenta running inside the diagram. So when you compute the imaginary part of this diagram, the dashed line is real, and so you simply have to look at the imaginary part of the bare propagator, and that gives the delta function in the energies. And so you can readily see that in order to have a non-zero contribution, you have to satisfy this delta function, and this can be satisfied either if q is equal to 0, but this is somehow trivial. So q equal to 0 means that the electron is moving without any scattering event, so the potential is not doing anything. And so this is really not the interesting part for the localization that we are interested in. But actually, the non-trivial part is where Q becomes equal to 2K. And this is simple to understand, because what you're saying is that the electron simply gets backflipped and comes back from where it was coming from, okay? And so this is the part responsible for localization. And so you impose that Q is equal to 2K, and then the integral is trivial. And you get a localization length that scales that is proportional to S of 2K, evaluated at 2K. This is what you would get for any kind of disorder, okay? But what the stealthiness gives, which is non-trivial, is that this S of 2K can be 0, because if it lies in that region where we set it to be 0, you have no contribution at this order in perturbation theory, and so you have to look at the higher order term. So you can see that this contribution is proportional to W squared, which is what you would get in the usual case. If this one is 0, you would get something different, and this is what we find quite interesting. So you can go at the next order. I don't go into the details here, but you get a different condition for having backscattering at the second order in perturbation theory. And if you find a solution to this, if you find a non-zero contribution to these diagrams, then it would mean that the localization length now scales with W to the -4. So it means that the localization length has become bigger. You can keep doing this. I will not go into the details, but basically you have to look at all the diagrams and try to figure out where they will have a contribution or where they will have not contributions. And then you find a diagram like this one. Let me explain a bit what it means. So on the x-axis, we have the size of the region in which S of k is equal to 0. So if you want is k naught, which goes between 0 and pi, or chi that goes between 0 and 1/2. So on the far left, you have the uncorrelated disorder, the usual disorder that you would expect. And on the far right, you have the lattice. And then on the y-axis, I have the momentum of the particle that is running into this 1D chain. So you can see that if you set k0 equal to 0, so the usual disorder, the localization length always scales like W to the -2. This is the usual result that you would expect. But then if you increase chi, depending on the energy of the particle, you can get different scalings. And actually you can get all the scalings with an even power. And this is quite interesting, because basically it's telling you that you're not able to defeat Anderson localization in this way, in the sense that the localization length is always finite, but you can make it as large as you want without sending the disorder strength to 0, which is that in general is the only way that you have to make the localization length bigger. Here you have another parameter, how correlated is the real space potential, and that is able to change the scaling. So this is, to us, it was quite interesting. And notice that you can have weird regions in which you can jump between W to the -2 to W to the -6, or W to the -4 to W to the -8. So you can skip orders in perturbation theory in a quite non-trivial way. Let me also show you that some numerical results in which you can actually see that this is the case. So let's focus, for example, to a particle with a given energy. So we are looking at a specific energy in the spectrum of the model. And if you compute the localization length at that energy, you would get the following. So you can see that here on the y-axis, I have the localization length in log scale. And so you have a region for small chi, so close to the uncorrelated case, in which for different W's, you have different values of the localization length, but it's basically of order 1. And then at some point, it quickly jumps to a much bigger value. And we are going from order 10 to order 1000, so it's a very big jump. And the position of this jump is the one predicted by our perturbation theory. And the same thing happens once again, where another transition is predicted to occur. And here the localization length becomes so big that even like numerical diagonalization is not able to detect the presence of a finite localization length. You can also look at the scaling of the localization length in these regimes. So now you fix chi and you see how it changes with W. And you see that for small chi, it's W squared, as the perturbation theory predicts. And then all of a sudden, if you change chi, all the curves align with W to the minus 4. And actually here, later on, we did some better numerics, and you can also see the W to the minus 6. So this is quite interesting, and I'll conclude by summarizing what I told you in one sentence. So basically, this hyperuniform disorder, this stealthy disorder, is able to make the system effectively delocalized in the following sense. If you take a finite but large system size, so you're not taking the thermodynamic limit first, this is relevant for all experimental applications. You can fix W, the disorder strength. You can keep it quite small, but not vanishingly small. Then for a fixed energy, you can find the value of chi, so a size of this stealthy interval, for which all the terms in the perturbation theory vanish up to a given order, m, that you can decide what it is. And in this way, the localization length will be able to exceed your system size. So it's not a delocalization in the thermodynamic limit. It's not a new phase, if you want, but it's something that for all practical purposes can be quite interesting, because it's a way of engineering disorder to obtain the properties that you like in an experimentally realizable fashion. So let me just thank you for the attention, and let me quickly present you the collaborators on this problem. Boris Altschuler is a well-known guy in localization that was working at Columbia, now is retired. Jonas and Mikhail were at Penn State. Now Jonas moved to MPI-PKS. And actually, Mikhail and his group are working on experimental verifications also of these results. And then Paul Steinhardt and Sal Torquato are my advisors here at Princeton. And you can find the preprint containing the results that I presented you here in this at this archive number or with the QR code. Thank you so much for the attention.
Thank you very much, Carlo, for this very interesting presentation, and maybe there are questions.
I have a question, Giuseppe.
Please,
Yep.
Andrea.
So nice presentation, very interesting. So just let me go back to the stealthy hyperuniform point processes.
Yeah.
I have difficulty to understand how you can generate, because in your case, W is a continuous parameter, so you can clearly create a Gaussian, basically a Gaussian field with this power spectrum, because you have the Wiener-Khinchin theorem making, which is necessary in sufficient condition to generate, so every non-negative spectrum can be realized. But I don't understand really in point processes, how can you create a structure factor that is 0 for a finite range around 0, because this means that you can partition the system in cells such that in all cells, in different cells, all the moments of the mass, so the mass, center of mass, inertia, tensor, etc., multitensor, etc., are all conserved. So I don't really understand how can you create a disordered system, a disordered point process with zero structure factor in a finite interval around 0.
So, okay, thanks for the question. It's a very good point. Let me just specify that when we are able to create these point processes, actually the one that I showed here, this one is a stealthy system, is the ones that look more ordered. So the system is not really divided into cells, where you can create these point processes within a fundamental cell. And then if you want, you can replicate that fundamental cell. But actually the structure factor, this one that you get, is the one for points within a fundamental cell. So there is no symmetry or translational symmetry, even discrete in this point process. And the way we do it is basically through gradient descent. So we start from a random initial point configuration, and then we assign a potential, which is that contains the structure factor. So the potential is defined in Fourier space, and the potential is basically the sum of the product between S of k, the one that you would like to have, and a function which is non-zero only in the region where you want S of k to be 0. And in this way, the ground state of that potential, where otherwise it would be always positive, but the place where the potential becomes 0 is only if S of k has this form here, so that it's 0 here, and then can be something else outside, but in that case, the function multiplies S of k is vanishing. And so the process is really simple. We start from a point pattern, we define this potential, and then we do local moves, like in gradient descent fashion, and we accept the moves if the potential is reduced. And let me just mention that we can obtain point configurations up to a few thousand point particles in, let's say, periodic boundary conditions, both in 2D and 3 dimensions, with the structure factor that is 0 up to the machine precision, so 10 to the minus 20. So it can be done, and it's actually a very precise technique for doing it.
Yeah, but my question is if you can demonstrate that it exists, okay, that you can get very close, I'm pretty sure, but okay, it's a mathematical problem.
Yeah, so from the very formal problem, I don't know if, I'm not sure if there are proofs that they exist, but there are proofs of some properties of this system. So somehow assuming that they exist. And one of the properties, for example, is that you cannot have arbitrarily large holes in these configurations, while here you can have arbitrarily large holes. And that is proved mathematically. But yeah, the constraint that gives you the stealthiness is not really the fact that you have to constrain all the moments, but is more of a global constraint, and it translates into a long-range correlations between the points.
Okay, thank you. Thank you very much.
Okay. If there is another short question, maybe we can have that. Otherwise, let's see. Yeah. I don't see.
I can maybe stop sharing. Okay.
Yeah. And since we have another meeting now, I think we can stop here. And I want really to thank both the speakers, Carlo and Clarissa, a lot for these very interesting talks, and happy Christmas and Merry New Year to everyone, and bye-bye to everyone.
Thank you.
Okay.
Bye-bye.
Ciao.
Bye.
Ciao. Ciao.
Ciao.
Bye bye.
Bye-bye.
Ciao a tutti.
Ciao.
Ciao. Ciao. Ciao.